divided by the average, which is the expected value of x squared or xt, power xt squared. Right, so the average power is signal, and the peak power, the ratio is really high for OFDM signals. Right, so this is defined as the peak to average power ratio. Now what happens here is that when we design an electronic circuit, hardware circuits have got limitations. What are the limitations? It has got range limitations. It can only support a range of voltage levels. You don't have hardware components that can have a unlimited voltage range from nanovolt to gigavolt, right? So it's very high level of limitations with electronic devices. Then that's the just going a bit of off track here. That's the current physical limitation in technology. Your electronics is very limited now because we've kind of used the max out of the current electronic technology, semiconductor technology. So the next generation, or the future generation, I suppose, is photonic technology, where you use, instead of electrons, you use photons to develop components and systems and so on. And that's where, based on photonics technology concepts, then you develop quantum computers and quantum systems and quantum communication based on photons. Right? Coming back to this topic, our electronic systems are very limited. How? In this case, voltage is very much limited. So when we design a receiver or a transmitter with voltage levels limited, if the peak voltage is really high compared to the average voltage, then that will clip the signal, and when the signals are clipped, you get nonlinear effects in the signal. That means that you won't maintain the same frequency components. So when you have nonlinear effects, you get multiples of frequencies, and that's not good for communication, because you rely on precise frequency for communication. So that when you receive, you would know what the frequency is. If your frequency is different, A, you're not going to recover the signal, B, you're going to interfere with other signals. So you get into double trouble because you can't recover your own signal. At the same time, when you interfere with other signals, you've got to pay a fine. All right. So this peak to average power ratio, defined by this simple equation, is a big problem for OFDM. When OFDM was implemented or invented and developed and so on. But now it's very well addressed. There are several techniques that are used to manage peak to average ratio very well. Not necessarily better hardware, but better solutions to distribute these signals over time, so that the peak to average power ratio is reduced. So in this problem, question 2, it just asked to calculate the peak to average power ratio. So the story, the background is for you to understand what's the issue with the peak to average power ratio. So calculate the peak to average power ratio in dB for the following OFDM signal sample sequence. So the sample sequence is given in the discrete domain. So that's pretty much what I've drawn here in the continuous domain. And we just need to calculate the peak to average power ratio for this set of samples, and signal samples, OFDM signal samples in the time domain. So let's do that. So for us, xn is given by 1.2 minus 0.3, 4.6, 0.2 minus 2.5, minus 1.8, 7.2, and 3.1. So that's given in the tutorial. So our peak to average power ratio is that, PAPR. So we need to calculate the maximum of x squared, the power of that, and the expected value or the mean value or the average value of the signal samples. So the maximum So what you could do is just first calculate x squared n of xn squared. That will give us certain values. I'll just quickly write down those values. 0.09, 21.16, 0.04, 6.25, 3.24, 51.84, and 9.6. Okay. So you just basically square these and you'll get these values. So that's xn squared. So that's an indication of your signal power. Right now, x is your signal, x squared is your signal power or the absolute value. Now we consider in voltage or these are voltages actually. For actual voltage levels, the power is also related to your load as well, or in other words, the resistance or the load itself. But in this case, we consider we don't need the knowledge of the load because we just simply assume that it's a normalized load. All right. So that's your xn squared, and therefore your max of x squared n is what was that, 51.84, and then your average, which is expected value of x squared, is the summation of x squared n divided by the total number of samples. So you sum this up, or you take the average of this xn squared. You should get an answer of 11.71. So this is the max of that of the power of the sequence, sample sequence, signal sequence. That's the expected value of the average, and then you just substitute into PAPR, and PAPR in dB. It's basically 10 log base 10 of 51.84 on 11.71. Should be around 6.46 dB. Okay. So that's 6.4 means like 4.5-ish. The maximum value is 4.5 times the average value. So let's see. So once you understand this PAPR for a particular type of OFDM signal, then you can design your receiver requirement in terms of the electronic components and whether PAPR would be an issue or not. Okay, so it's a straightforward problem, but it's important to understand where the problem comes from. Any questions on that? Okay, good. All right, so there's a quiz. First, and the reason why I had it as a quiz is to make sure that you'll give it a try. So let's try and do this. Now this connects our week 4 small scale fading and the consequence of small scale fading in OFDM systems. So we did a similar problem in week 4 tutorial related to small scale fading. So if you remember, in small scale fading there are 2 main causes. One is the mobility that leads to Doppler effect, and then the multipath component. The second one is the multipath component that leads to time dispersion. Right? So the time dispersion, the multipath effect, gives us a particular parameter for the wireless channel, which is known as the coherence bandwidth. So that's the bandwidth where the wireless channel passes through the frequencies from the signal. That's the coherence bandwidth of the channel. Right? So here we have a wireless channel with a multipath effect. That means that it has got a coherence bandwidth. Just need to understand, with an OFDM system, if a subcarrier passes through that limited frequency range, whether the subcarrier is going to undergo frequency selective fading or flat fading. Right? So if your subcarrier bandwidth is greater than the coherence bandwidth of the channel, there will be a frequency selective fading because the channel will cut off a lot of frequencies of the transmitted signal. If your subcarrier bandwidth is less than the coherence bandwidth, that means the channel will pass through all the frequency components of the subcarrier. So that's the question here. So we have an OFDM system with 20 megahertz spectrum. So the total spectrum available is 20 megahertz. And the number of subcarriers is 1024. So you can calculate the subcarrier spacing for that, right? So that's 20 megahertz divided by 1024 will give you the subcarrier spacing. So if the multipath wireless channel has a delay spread of 20 microseconds, so that's the delay spread due to multipath effect, right? RMS delay spread of 20 microseconds. Identify whether the OFDM system will experience flat fading, flat or frequency selective fading in the transmission for 90% frequency correlation. Now, the calculation of the coherence bandwidth, we have two levels of coherence bandwidth calculations. One is the 90% frequency correlation bandwidth, that is over the range of frequencies, or 90% of the frequencies will be passed without any effect. And we also have something called the 50% frequency correlation. In other words, 50% of the frequency components will be passed without any degradation. So accordingly, we can calculate the coherence bandwidth. We open up V4 lectures. Sorry?
Page 37.
Page 37. So that's week 4 lectures. So that's multipath fading, and then that leads to coherence. That's the time dispersion due to multipath effect, and it's page 35. The 36, 37 is where you're right. So it's the frequency selective or the flat fade. So these are the two expressions for the coherence bandwidth of the channel, right? Coherence bandwidth of the channel. 50%, 90% frequency correlation is given by 1/50 sigma tau. Sigma tau is the RMS delay spread calculated here, right? That's the delay spread, how much spread it has got. And for 50% correlation, the coherence bandwidth is much higher. So in other words, if this is the response of the channel, this is your coherence bandwidth for 90% correlation. So very strictly 90% of the frequencies will be passed through this. And the 50% coherence bandwidth will be this in the red. Right? So half of the frequencies will be undergoing some level of variation. That's what it means, 50% correlation and 90% correlation. So in the question, it asks for 90% correlation bandwidth, which means that we've got to pick that equation to calculate the coherence bandwidth. BC is 1 on 50 sigma tau, and sigma tau is given to us. Sigma tau is given to us as 20 microseconds. All right, so I'm going to stop there and give you 5 minutes to see if this is going to be a frequency selective or a flat fading channel. Give it a try, please. As I mentioned, you just need to calculate the 90% coherence bandwidth first, and then see how that compares to the subcarrier width. Okay, good. I think the problem is, the question is pretty, it's easily asked in three lines, right? But the concepts behind the question goes back to various topics. So that's the whole purpose. You need to understand small scale fading and the concept of coherence bandwidth, and then you need to understand OFDM, and then try to connect that with the propagation effects. Right? So how many of you all got flat fading? Okay, that's good. Because it's frequency selective fading, right? So just show the solution here without doing the calculation. So the subcarrier frequency is 20 megahertz divided by 1024 subcarriers is 19.5 kilohertz, right? So that's the subcarrier spacing. So in other words, you have 1024 subcarriers, over 20 megahertz frequency, and the subcarrier spacing between the subsequent adjacent subcarriers is this delta F. Right, and the coherence bandwidth is for 90% frequency correlation is 1 on 50 sigma tau, and sigma tau is given as 20 microseconds, and which is 1 kilohertz. So 1 kilohertz is the coherence bandwidth for the channel, which is pretty bad, and therefore this will undergo frequency selective fading. So one of the
it's because the subcarrier spacing is larger.
correct, yeah. So that's right. So your channel coherence bandwidth is 1 kilohertz, and subcarrier spacing is 19 kilohertz. 19 kilohertz. So most of the signal frequencies will be distorted. So therefore, it will be a frequency selective fading. Specific frequencies will be selectively faded compared to a flat fading if your subcarrier is less than 1 kilohertz. So if you're transmitting a signal, if your frequencies are not retained, and the weights of the frequencies are not retained at the receiver end, that means you won't recover the original signal, right? So, and therefore it will be a distorted signal. So we haven't covered equalization in this course. That's a well-treated topic. And equalization is a process that compensates for the changes, variations in the frequency to combat frequency selective fading. And if the channel is varying very fast, that depends on the Doppler, the other effect, then your compensating process will also need to be really fast as well. Okay, so that concludes the topic on OFDM. And you can really see that the questions or tutorial problems that we address are really some, I would say, conceptual and basic compared to the actual topics covered in the lectures, right? So the reason for that is, you need to understand the topic properly, but the questions asked here is pretty much testing the basics. And in your final test as well, you won't be getting really hard or in-depth questions related to OFDM technology itself. That's not the purpose of this course or the objective of this course. The objective of this course is for you to understand design of mobile and wireless communication system. For the design aspect, you need to understand the technology. So the testing will be on the design part of the technology, but not the technology itself. Right? So we can have half a course on OFDM technology itself, its pros and cons and issues and design and so on, which is not the objective here. We do treat OFDM in some of the other courses as well. I think, I'm not sure if still the DSP course covers OFDM. All right. Let's move on to week number 8 problems. And that's a topic on error correction codes. Right. Now let's do a bit of a warm up on that as usual. Error correction codes are also known as channel coding. So you code the signal to suit the particular channel or to combat errors in the particular channel. Right. Now, again, this is a very broad topic that spans across communications, information theory, and mathematics in terms of linear algebra and another topic called spaces, vector space, and so on. Right? So space in mathematics is a very unique topic that covers a lot of applications, including error correction codes as well. So you define a space in a mathematical space, and then you can define mathematical properties, operators, and so on. And it's applied for many fields, such as obviously outer space studies as well. So channel coding, error correction codes, it's got various forms. Waveform coding, you transform a signal waveform into another waveform to combat errors. We are not covering that in this topic. Sequence coding, and we will be covering sequence coding in this topic, structured sequence. And in particular, we'll be looking at binary sequences. So sequence coding, and then specifically binary sequences, which is pretty much zeros and ones, right, instead of any other sequences. And within binary sequences, zeros and ones, there are other classifications as well, block codes and cyclic codes. And we're only covering block codes. So you can see how much focus we are in this course, because otherwise error correction codes and channel coding can be taught across 2 semesters in 2 courses. That's how big the area is. So we'll be looking at block codes, and specifically in block codes, we'll be looking at something called the systematic codes, which covers a particular property, set of properties of block codes. Right? So that's what we'll be learning, covering in this. Now again, we won't be we won't be testing, how block codes really are generated and so on, apart from how we generate block codes in terms of the generator codes, generator matrix, but mostly how block codes are used, or error correction codes are used for our design purpose in order to properly design our system. So in order to understand that, you just need to understand the concepts of error correction codes or block codes, right? Now it's pretty straightforward, and this is a simple example. This is your original message, right? 00, and then you group the message into either 2 bits or 3 bits or whatever it is, and then you add a redundant bit, so that with the redundancy, with the added redundancy, you will be able to better detect the bits or the words as we call. Right? So this is called error correction code. Now, the redundancy, the amount of redundancy that you bring in, better the correction capability or ability would be at the receiver end. Right? Now, a simple example here is something called a repetition code. Right? So you got you're going to transmit 0 or a 1, right? Instead of transmitting a single 0, you transmit 10 zeros. So that's, you repeat the 0 10 times. And likewise, instead of transmitting a 1, you repeat 1 10 times. Now that's common sense, right? Repetition code. But in theory, it's called repetition codes. So out of the 10 transmitted bits, your ability to detect that particular bit 0 or 1 is much higher than with a single bit. Those 9 extra transmission bits are called redundant bits. Right? So how much redundancy you want to add in, whether it's infinite or finite, obviously it has to be finite, is the design, is a trade-off. Because the amount of redundancy you add means that you're trading off for the capacity of the original information, right? So you want to send something, but you're putting a bulk of redundancy in there, so the amount of actual throughput is reduced. For deep space communication, you put a lot of redundancy, because by the time, because there's you know, no one's going to have a HD video transmission from deep space to here, right? It'll be just maybe image, HD image still, but not in real time, in other words, right? So, so those all those things are kind of considered in designing or adapting a particular type of code, error correction code. Now, when you add redundancy, your data rate, effective data rate changes as well. So K is the number of bits that you group together to form an n-bit code word, right? So n minus k is the number of redundant bits, right? And the code rate is defined by k on n, right? So if 2-bit message is coded into a 3-bit word, then it's a 2 on 3 coding scheme, or 3, 2 coding scheme. So you've got to be careful. These are the two ways that you can represent an error correction coding scheme, either k on n or n, k, right? Both mean the same thing, but the k and n are swapped around in the terminologies or definition. So you've got to be careful, right? So this is the code rate, and that's a notation for particular type of coding. Okay. So your data rate will also change. This is the original rate, RS, and your coded rate is RC, which is n on k. Right? So it will be an increased coded rate. So these are all important aspects. Now, I don't want to take actually a lecture now, because we need to complete these tutorial problems. So accordingly, we will have a change in bit energy as well for the coded system versus the uncoded system, because your data rate changes while the power remains the same. Okay. An important model that we adopt for error correction codes is something called the binary symmetric channel. All right, a binary symmetric channel is a channel. So this is similar to the wireless channel model that we adopt for zeros and ones based transmission, right? We adopt a channel model called the binary symmetric channel. So the binary symmetric channel what it does is, we have an input sequence X, zeros and ones coming in, that's the transmitter side, and Y on the receiver side, whatever it's decoded. Whatever is in between, it's your channel, right? In zeros and in a binary form. So if you transmit a 1, the likelihood or the probability of the 1 becoming an error or a 0 is P, right? Likewise, if you transmit a 0, the likelihood of 0 becoming a 1 has also got the same probability, P. So that's why it's called a binary symmetric channel. A 1 becoming a 0 or a 0 becoming a 1 has got the same likelihood, right? And a 1 becoming a 1, therefore, is 1 minus P, and 0 becoming a 0 is also 1 minus P. So this channel model, or this channel, is known as the binary symmetric channel. So what is this P? Sorry? It's a probability, yes, but based on your modulation technique, this is your bit error probability, isn't it? The bit error probability is the probability that your bit becomes and undergoes an error at the receiver side and becomes a 0, or 0 becomes a 1. Right? So if you're using a QPSK, you know how to calculate the bit error probability of a QPSK, and that's this P, the same thing as this P, right? But in the channel perspective or terminology, this is known as the transition probability. P, 1 becoming a 0 is P, and 0 becoming a 1 is also P, all right? Now, if we, now this takes us to a bit of probability and statistics fundamentals and theory. So if we have a group of bits, let's say n bits transmitted through this binary symmetric channel, right? So n block of bits transmitted through binary symmetric channel, and we receive n bits at the output, right? We will be receiving only n bits at the output because this is known as a linear channel, right? So if n bits transmitted and received in this binary symmetric channel, the output, that is the n bits, the probability, so AI is the transmitted block of bits on the transmitter side, and B is the received bits, right? Now if B is the same as AI, then no bit errors would have happened, right? If B is same as the AI. But with the binary symmetric channel, the chances are B is not going to be the same as AI, right, on average. So the probability of receiving B, given that some AI was transmitted for an n-bit block, is this. That is, T is the number of bits in error, right? So number of bits in error. So that has got the probability of a bit becoming an error is P. So P to the power of T. So T number of bit errors, and n minus T number of no bit errors. So the probability of no bit error is 1 minus P. So n minus T number of bits becomes whatever was transmitted or received. Right? So this is the probability that we receive B given AI was transmitted, given that T number of bit errors occur. Okay? All right. Now, Hamming distance is an important, let's say, KPI or a measure in binary symmetric or binary codes. Right? Now, Hamming distance is actually, if you have two code words, A and B, so A is 1001111 and B is 111011. The Hamming distance is the differences in the bits between A and B. So if you take the first bit of A, 1, the second bit of B is also 1, there's no difference. The second bit is different here and here. The third bit is not different, fourth is not different, fifth, sixth are the same as well. So only one bit is in difference between A and B. So that's the Hamming distance between A and B, right? So Hamming distance gives us the number of bits that are in error. For example, if A is transmitted and B is received, the Hamming distance basically says that how many bits have undergone transition, right? Because the difference is in the number of bits. All right. We talked about binary symmetric channel, talked about the probability of receiving a B given AI was transmitted. So with error correction codes, which we'll cover in the next few slides, with error correction codes, you can either detect errors that have been occurred during the transmission and or correct errors as well, right? So the, the, the strength of a particular coding scheme depends on how many bits it can detect, bit errors it can detect, and how many bit errors it can correct. There are coding schemes that can, with a lot of redundancy, you can correct more bit errors compared to another coding scheme with less redundancy in the coding scheme. So that's more the redundancy you have, better the correction ability will be. The Hamming distance, the minimum Hamming distance of a coding scheme is an indicator of how the strength of the coding scheme. So if you calculate the Hamming distance, if for example, if it's 5, then it can detect up to 4 bit errors, right? And if the Hamming distance is 5 for a particular code, it can correct up to 2 errors, 2t, right? It cannot detect 3 errors because this is the rule that that applies to linear block codes, right? So the Hamming distance is a good measure of the strength of a particular coding scheme. Right, this is a good example as well. We'll probably go through this. So we have a 3-bit code word, x equals 0, 0, 0 and 1, 1, 1. This is on the transmitter side, right? Now, and correspondingly on the receiver side, it receives at x hat, either 0, 0, 0 or 1, 1, 1, right? Now, so this on the transmitter side and the receiver side, the way that it decides whether it's x hat or x hat 000, x hat 11, is it counts the number of zeros or ones and say that if the zeros are more than the ones, then it says it's a 0, 0, 0. If the ones are more than zeros, it says it's a 111. That's basically the repetition code. You make a decision on how many zeros are there in the word, and then you decide that. This is a particular type of coding scheme, right? Now that's just the background to this. Now, how do we calculate the probability of bit error or coding error for this would be an interesting task, and that will help you to understand how error correction mechanisms will work and so on. So 000, when 000 is transmitted, right? If it receives as 000, then not a problem. It says 000. If 000 is transmitted and if the received is 001, 1 bit error has occurred, it will still say that it's 000, right? So in this case, what happens is that it has corrected 1 bit error. Why? Because it's 00001, but it says that, all right, I got more zeros, but therefore it should be a 0. It should be a 000. Right? So it says that the 1 has turned into a 0. So that's the concept or fundamentals of error correction. So you define a code word that could basically, when you detect it, you automatically correct the errors in there. Right? Now, repetition code has got really good strength. Now, if the repetition is 5 times, then you can correct more bit errors. So here, if 000 is transmitted and 010 is received, then it still corrects 1 bit error. Still correct 1 bit error, and again still corrects 1 bit error. So this error correction code can correct up to 1 bit errors. if 2-bit errors happen, what will happen? If 2-bit errors happen, these are the outcomes, right? The second 2 bits become 1. Can it correct? It can't correct. Why? Because it said I got more ones than zeros, so I'm going to decide on 111 instead of 000. So that error still happens. It's an error, right? It doesn't correct. So the strength of this code word is basically 1-bit error that could be corrected. It's the same for when you transmit x equals 111. All these cases, it can correct up to 1-bit error. All the zeros, 1-bit zeros can be turned into a 1. And any double zeros, double errors, in this case, is errorly decided as 000. This is the concept of error correction mechanism. This is an easy example, or probably the easiest one to understand how it works, right? There's another example at the end of the slide as well. You can have a look at it. We can also calculate the probability of error as well. So we have, so what is the probability of receiving this given that? Anybody?
1 minute.
Sorry?
1 minute.
1 minus p
P.
to the power of 3. Why? Because 3 bits. So the first bit has got a probability of becoming 1 minus p into a 0, probability of 1 minus p into a 0, and probability of 1 minus p into a 0. So receiving this code word, given this was transmitted, is 1 minus p to the power of 3. This one, 1 minus p to the power of 3 times p, because 1 bit error has occurred. And the same thing as this. 1 minus p, 1 minus p, p. 1 minus p squared, p. And then again 1 minus p squared, p. Right? And the same thing will happen here as well. And then if we combine the probabilities, the probability of error for this coding scheme can be easily calculated. Using, so we're pretty much using this equation here, right, to calculate the block error. All right, the other, so this is the equation, it's a binomial density equation for calculating the number of, or the block error probability given your, of a n-bit code word, you have an n-bit code word with a transition probability of PC. So transition probability is your binary symmetric channels transition probability, which is the same as the bit error probability of your modulation technique, right, PC. That can correct up to U errors, right? So up to U errors, there will be no, up to U bits, there will be no errors. So anything from U to N errors, it cannot correct. The error correction code cannot correct. So we need to calculate the probability of block error for the bits that, number of bit errors that occur within that block. So if this is a 10-bit block, and let's say 3 bits can be corrected, right? We need to calculate the probability of 4-bit errors happening, that is U plus 1, 4. 5 bits happening in that 10 block, 6 bits of error happening in that block, all the way up to 10 bits error happening in that block. So that's what this summation stands for. And this is the combination of the bit positions that it can happen, right? It can happen in any combination, right? 5 bits in error can happen in different combinations. That's the combinatorial expression, NCJ. Okay, so this is the probability of block error equation for a block of n bits and an error correction mechanism that can correct up to U errors. If there are no error correction mechanisms, then U is equals to 0 because it cannot correct any errors. So you got to calculate all the errors. Any questions? Now these are okay, so these are different types of coding mechanisms. The uncoded, without referring to, so there's no coding case, Hamming with 4-bit groups, group of bits, coded into 7-bit word, redundancy of 3 bits. Another Hamming, redundancy of 4 bits. Another Hamming, redundancy of how much? 5 bits. Right? The t equals 1 means that the number of bit errors it can correct. Number of bit errors this can correct and so on. You can see here, BCH codes is one of the powerful codes. It takes about 36-bit word and converts into 127 code words. So there's a lot of redundancy. But it can correct up to 15 bits. So depending on the application, we can deploy the different types of coding scheme. And if you look at the bit error probability graph with EB on N0, the typical graph that we see for modulation techniques, the blue one is the uncoded error, uncoded QPSK, I think, or BPSK, and the BCH 12764 is that. It's very powerful, you can see. The trade-off here is that it'll have a lot of redundancy, which means that less information will be shared. But in most applications, that's not a problem because our bandwidth is so high now compared to the original data rate of the application. Whether it's video or voice, our bandwidth is so massive, we can introduce a lot of redundancy and then get more accurate recovery of information. All right, let's stop there. And then next week we will attend to these problems. And next week will be the last week. So we'll try to finish week 7 and then we'll see how we go from there. All right, I'll see you all next week.
Have we got the exam dates?
Sorry?
Have we got the exam dates? The temperature.
Yeah, it should be. And I think it's in here as well.